how can something with absolutely no mass actually push on something else, exert a force?
Yeah, it's one of those ideas that just throws your intuition for a loop, doesn't it? I mean,
Yeah.
in our world, force feels like pushing something solid, something with substance, with mass resisting you. We're just so used to thinking FMA.
Totally. You picture force needing that mass, needing inertia to act against. But digging into the material for this deep dive, we're focused on the photon light's fundamental particle, and it has zero rest mass. Zip.
And yet it definitely exerts a force. That's not up for debate.
Right.
And that apparent contradiction, and that's exactly what we're going to unpack today. Our mission really is to figure out how these massless little packets of energy photons actually manage to push things around.
And it seems like the answer doesn't just challenge our concept of mass, it also forces us, to think about force itself a bit differently.
That's exactly right. Look, our classical picture, FMA, force equals mass times acceleration. It's brilliant for, like, baseballs and cars and planets. Incredibly useful.
Sure, standard physics.
But when you start dealing with particles zipping along at light speed or systems where mass might not even be constant, well, that simple formula isn't the whole picture.
Okay.
The more fundamental definition, going back to Newton really, and the one that's key here, is that force is the rate of change momentum. F equals dp dt. Change in momentum over change in time.
So force isn't just about making mass speed up and slow down. It's about changing its momentum, whatever that momentum comes from.
Precisely. Now, classically, we think momentum P is just mass times velocity, right? P
Yeah.
d.
Right.
And for everyday objects, if the mass stays the same, changing momentum does mean changing velocity, which is acceleration. So FET-PDG just becomes FE time times dV/dt, or FNA. It works out.
Okay, connects back.
But that whole PMV idea just plain doesn't work for light itself. For photons moving at c, they don't have the m in that equation.
Okay, yeah, here's where my brain starts to hurt a little. If photons have no rest mass and PMV is out, how on earth do they have momentum? That feels like the core problem here.
And that's where we really have to step out of the classical world and into the quantum one, building on work from Planck, Einstein.
The pioneers.
Absolutely. What the sources we looked at clearly show is that photons are these discrete packets or quanta of energy. We know their energy, E, is tied to their frequency, F. E equals hf, where h is Planck's constant.
Okay, energy depends on frequency or color.
Exactly. And here's the revolutionary bit. Even though they're massless, photons absolutely carry momentum. And that momentum isn't tied to some non-existent mass. It's tied directly to their energy.
Wait, so for a photon, it's the energy itself that gives it momentum, not mass times velocity, but energy.
That's the fundamental insight. The momentum, P, of a photon is given by a really elegant little equation. Key equals EC. Momentum equals its energy divided by the speed of light.
P.
Or, if you prefer thinking in waves, since EHF and frequency times wavelength, lambda is c, you can also write it as P equaled as a cook. Momentum is Planck's constant divided by the photon's wavelength.
Huh. So higher energy photons like blue light or gamma rays with shorter wavelengths, they have more momentum.
More. Oof. They absolutely do. More energy means more momentum. It's directly proportional. Their push is related to their energy level, their color, so to speak.
That's fascinating. The energy is the momentum, just scaled by c. Okay, so bringing this back to force. How does a photon having this energy momentum translate into actually pushing something?
Right. So that brings us squarely to the concept of radiation pressure, which the material explains quite well. Remember, force is the rate of change of momentum, F dp dt.
Okay, got it.
So when a photon hits something, say a mirror, a solar panel, even your hand, it interacts. And in that interaction, it transfers its momentum to that surface. By changing the momentum of the surface, the photon exerts a force on it, like a tiny, incredibly fast, massless billiard ball hitting it.
A momentum delivery service.
You can put it that way. And the sources talk about two main scenarios. Scenario one, the surface absorbs the photon, like a black surface.
Okay.
In that case, the photon just stops, gives up all its momentum P to the surface. The surface gains momentum P.
That's simple transfer.
Simple transfer.
Yeah.
But scenario two is even more interesting. Reflection. Imagine a perfect mirror.
Okay.
The photon hits, bounces off, its direction reverses. So its momentum goes from, say, plus P to may P.
Oh, right. Velocity reverses.
Well, its direction reverses, so its momentum vector flips. The change in the photon's momentum isn't just P, it's P minus negative P, which is 2P.
Double.
Double the change for the photon. And because momentum has to be conserved overall.
The surface must get that 2p kick.
Exactly. A perfectly reflective surface feels twice the force from the same incoming light compared to a perfectly absorbing one, because you're not just stopping the momentum, you're throwing it back.
Wow, okay. That makes sense. You're causing a bigger change in the photon's momentum, so you get a bigger reaction force.
Precisely. Now look, the force from one single photon, it's minuscule, absolutely tiny. You'd never feel it.
Right.
But imagine sunlight. That's not one photon. It's trillions upon trillions upon trillions hitting every square meter every second.
A constant stream.
A constant stream. And that continuous transfer of momentum, photon after photon, adds up. It creates a steady, measurable force. That's what we call radiation pressure.
And the sources mentioned solar sails?
Yeah.
That's this effect in action.
That's probably the coolest, most direct application. The idea of using sunlight itself, photon momentum, to propel spacecraft.
Seems like science fiction, but it's real.
It is. You deploy this huge, incredibly thin, but highly reflective sail out in space. Think acres wide, but thinner than plastic wrap.
Wow.
The constant stream of photons from the sun hits this giant mirror, reflects off, transferring twice their momentum, remember?
Right, this two-peak kick.
And exerts this tiny, tiny push. But it's continuous. It never stops as long as the sun shines on it. No fuel needed. And over weeks, months, years, this relentless, gentle push can accelerate the spacecraft to incredible speeds, way beyond what you could easily do with just chemical rockets for certain missions.
That's an amazing example. It really grounds this abstract idea of massless momentum transfer in something tangible, or, well, almost tangible.
It's a direct, large-scale demonstration. But you're right, the core concept, something massless having momentum, it still feels so. Weirdly non-classical. Does relativity, Einstein's big theory, have anything to say about this? Does it fit in?
Good question. How does EMC-Hasse fit, or does it?
It absolutely fits, and in a really, really neat way. We always hear EMTR, right? Mass energy equivalence.
Famous equation.
But the source material rightly points out that's actually a simplified version. It's the version for an object at rest. The full equation from special relativity, the one that includes motion and momentum, is EOTP plus E.
Okay, whoa. E squared equals PC squared plus M naught C squared squared. That looks a bit more complicated.
It does look a bit intimidating, but let's break it down. E is the total energy, P is the momentum, C is the speed of light, and M, that is the rest mass, the mass an object has when it's not moving.
Okay.
Rest mass.
So for particles that have rest mass, like an electron, a proton, you, me, this table, both terms contribute to the total energy. The PC part relates to its energy of motion, and the M aerosol part relates to its intrinsic energy locked up in its rest mass.
Right, like the original EMC watt. That's the rest energy part.
Kind of, yeah. It's embedded there. But now, think about our photon. What's its rest mass? M.
0. We established that.
0. So what happens to that equation? E, PC plus M aerosol P plus M euro. They could plug in M euro?
Well, the whole second term, the MEOSU part, it just disappears. It becomes 0.
Exactly. It vanishes completely.
And you're just left with the EPCU.
Which, if you take the square root of both sides...
You get EPCX, the EE equals PC. The exact same relationship between energy and momentum for a photon that we got from quantum mechanics earlier.
Wow, okay.
It's a profound result. It falls right out of special relativity. Completely independently, it confirms that for a massless particle moving at speed c, its energy and momentum must be related by EPC.
So relativity basically says if something is massless but has energy and moves at c, it has to have momentum.
That's what it implies, yes. Momentum isn't just some property exclusive to things with rest mass. It's something more fundamental, tied directly to energy and motion. Since photons always have energy, EHF, remember, and always move at c, relativity itself demands they possess momentum, PEHE.
Okay, that ties it together beautifully. It's not just a quantum quirk, it's baked into the structure of space-time and energy according to relativity.
Exactly. The quantum view and the relativistic view lock together perfectly on this point.
All right, so let's try and crystallize this. We've gone through quite a journey here. What are the main takeaways from this material that you think people should really grasp?
Yeah, pulling it all together. I think the biggest thing, for me at least, is that fundamental reframing of what force is, moving beyond just FMA.
Right, it's FDPDT, rate of change of momentum.
That's the core, and photons are the ultimate example of why that distinction matters. They show us, undeniably, that momentum isn't exclusively tied to rest mass.
It's tied to energy and motion.
Exactly. Captured by that quantum relationship, PEC or PA, and confirmed elegantly by relativity's EPC for massless particles.
And when these photons interact with matter...
You transfer that momentum. That transfer over time is the force. That's radiation pressure.
Which is tiny, but real and amplified by reflection, enough to push solar sails.
Precisely. So the past was kind of. Starting with that EFMA confusion, getting to the deeper FDPDT definition, figuring out where photon momentum comes from, PEC, seeing how transferring it creates force, and then getting that beautiful confirmation from special relativity.
It really does reshape how you think about momentum, doesn't it? It's not just for, I don't know, bowling balls or things with heft. It's fundamental to energy itself when it's moving. Photons just make it incredibly obvious because they only have energy and motion, no rest mass to confuse things.
Couldn't have said it better. They are perhaps the purest demonstration of momentum being linked to energy and motion.
And it's just such a powerful reminder, isn't it? How the rules down at the quantum level, the fundamental level, can seem so utterly different from our everyday world, our macroscopic experience.
Oh, absolutely. Our intuition is built on throwing rocks and catching balls,
Yeah.
not on analyzing individual photons. It needs recalibrating when we look at the universe's building blocks.
It's definitely counterintuitive, but like you said, once you follow the logic, the physics, it hangs together perfectly.
It really does. And maybe a final thought to leave you mulling over, something sparked by all this material we covered. If momentum isn't fundamentally about having rest mass, but rather about energy and motion, and if massless particles like photons demonstrate this so clearly, what does that really tell us about the deep-down nature of reality itself, where energy, momentum, space, and time seem to be so much more interconnected than we usually think?
That's definitely something to chew on, the fundamental connections.
Something to keep thinking about long after this deep dive.